All right, so a suburban high school has a population of 1376. So if I'm thinking of a Venn diagram, the entire number of students has to add up to 1376. The number of students who participate in sports is 649. So I've got a sports circle. The sports circle has to add up to 649, although it's potentially overlapping with music. So I don't necessarily know how that 649 is going to be split up, because I'm assuming some of those 649 do both, right? So likely the number 649 is not going to show up on your paper at all, but the two numbers here and here should add up to 649. So what we did yesterday was we just kind of did x plus y has to add up to 649. The number of students who participate in music is 433. So likewise, 433 is probably not going to show its face directly on the Venn diagram, but the two music sections, people who are just music versus the people who are music and sports, those two numbers, y plus z, have to add up to 433. If the probability that a student participates in either sports or music, so is 974 out of the 1376. So what has to add up to 974? Where are the kids that do either or? No. So, I mean, raise your hand if you play sports. Just sports. Just sports. Raise your hand if you would be an X. Okay? If someone said to you, do you either do sports or music in Hamburg, what would you say, yes or no? You'd say yes, right? You do. Raise your hand if you do just music. Nobody does just music? Okay, pretend you just played the trumpet and you don't do anything else in Hamburg. Okay, thanks, Haley. Haley, do you do either sports or music in Hamburg? Yes. Okay? So she would say yes. Raise your hand if you do both. Okay? If someone asked you, Georgia, do you do either sports or music in Hamburg, would you say yes or no? You would say yes. So when someone asks you an or question and you've done one or the other, and even if you've done both, you say yes is the correct answer. So the people who've done either sports or music are all of these combined. Okay? So x plus y plus z is 974. And so what we kind of did yesterday was really a pretty easy, this is a system in 3 variables, but it's not as long-winded of a process as we saw earlier in the year, because you can just realize, okay, x plus y equals 649. So I'm going to jump down here, and I'm going to replace this x plus y with 649 kids. And then I'm going to solve for z. So subtract 649, and z equals 974 minus 649. 325. And then once you have one of these numbers, life gets a lot easier, because then you can, if you know z is 325, we can go back and put the 325 there. We knew that the music category total was supposed to be 433. Now that z is 325, that's y plus 325 equals 433. So subtract 325 from both sides, and y is 108. And then we knew the sports circle was supposed to be 649 total. So if we go here, we know x plus 108 is now 649, and subtract 108. It's really the exact same, it reads differently, but the exact same process we followed yesterday in our notes, 541. So the only issue is now, and I haven't even read the question, but I like to complete my Venn diagram so I make sense of it all. All of these kids, 541 that do just sports, 108 that do both, and 325 that do just music, these add up to 974. Oh shoot, duh, I should have known that, right? So how many people do nothing? If the grand total number of kids is 1376, subtract the 974 that are at least in the circle somewhere. 1376 minus 974 on a calculator will tell you that 402 kids do nothing. Well, neither of those anyway. Yes? So what is the probability that a student participates in neither sports nor music? 402 out of 1376. Raise your hand if you got that right. 1, 2, 3, 4, 5, 6. Good. Next one. Totally different presentation. Number one, amen, we don't have to read a paragraph. But number two, it's like, but I don't really have much concrete stuff in the meaning, of a real word problem to wrap my head around. So we have events A and B. The probability of A is 0.6. The probability of B is 0.5. And the probability of A or B is 0.8. So, again, A, B. So A is comprised of these two sections. So if I go again and do X, Y, and Z, X plus Y has to be 0.6. Y plus Z has to be 0.5. And A or B, which would be X plus Y plus Z, has to equal 0.8. Quick system. X plus Y is 0.6, so that's 0.6. 0.6 plus Z equals 0.8. Z is 0.2, which makes Y what? If Z is 0.2, what's Y? 0.3. And if Y is 0.3, what's X? 0.3. And all of these add up to 0.8. So either or is 0.8, so what's nothing? 0.2, because Sierra, you know that your probabilities have to add up to, thank you so much, 1, right? If there's an 80% chance that they fall in a circle, there's a 20% chance that they don't. Just always has to add up to 100%. A little bit different. These give us raw numbers. This one was actually giving us the probability and not the raw numbers, but the same fill-in situation happens. So now to answer the question, probability of A and B is just 0.3. Raise your hand if you think you got that right. Good. 1, 2, 3. Okay. All right. On your homework, questions. On number 3, complements. Complementary events, Georgia, should add up to 1, the probability of them happening. Either one happens or the other happens. Those are your only two options. So the probability of A plus the probability of B needs to add up to 1. That's the definition of being complements. Which one of these is just a rearranged version of it? Okay? So essentially, if we want to get the 1 all by itself, we would have to subtract this P of A over. So that would be the probability of B minus the probability of A equals 1. That's not what that's saying, right? So that's no good. If we were to get 1 all by itself here, we'd have to add P of A over, and we'd get P of A, or P of B plus P of A equals 1. Probability of B, probability of A, add up to 1. That's your answer. Okay? This one you'd have to multiply by the probability of A, so probability of A times the probability of B equals 1. That's not what complements are. And this one you would have to, you could add your 1 over to the left and subtract your B over to the right. So it would be 1 equals probability of A minus probability of B again, which is not right. So it's just a rearranged version of the definition. And then lastly, on number 4, if a fair coin is flipped 3 times, the probability it will land heads up all 3 times is 1 out of 8. So before I go further, I would do, because it is not overly huge, I would do a tree diagram of 3 flips. The first flip is tails or heads. The second flip could then be tails or heads off of that one. Or if you got heads, tails or heads off of that one. And then the third flip, if you already got tails, tails, could be tails or heads. If you already got tails, heads, it could be tails or heads. And so on and so forth. So your number of outcomes is equivalent to whatever's in your bottom row. If your bottom row has 8 branches, there are 8 possible outcomes. If you then needed to list those, your whole avenue to get to each final branch would be your list of your sample space. So your sample space would be like tails, tails, tails. That would be one outcome. Tails, tails, heads would be a second. Tails, heads, tails would be a third, so on and so forth. And then you'd have 8 different avenues to get from top to bottom. And you'd kind of list those out. Okie doke. So which of the following is the probability that when a coin is flipped 3 times, at least one tail will show up? At least one means 1 could show up, or 2 could show up, or all 3 could show up, right? So every single one of these 4 has at least 1 tails because it starts with that, right? So this has at least, all of these have at least 1 tail if you trace it back. This one is a tail, so clearly it has at least 1 tail. Same thing with this one. This one isn't ending with a tail, but we have a tail in the middle, so that one counts as well. The only one really that doesn't is all 3 heads. So if you do it that way, you just got 7 out of 8. Something tells me one of the thought processes with asking this is for you to realize that if they want the probability that there's at least 1 tail, then that's the probability that it's not all heads, right? If you get at least 1 tail, then that means as long as it's not all heads, you're good. So the probability of all heads is what they told you. That's 1/8. The probability of not all heads is going to be the complement of that. You're either one or the other. You're either all heads or you're not. So 1/8 would have a complement of 7/8, and I think that that's probably the thought process that they wanted you to have, given that it's complementary events. They told you all heads, and they're pretty much asking you for not all heads. Okie doke. So, just as a heads up for scheduling, you're going to have a test on Tuesday. So we're still a week away, but it is not a long chapter, and I want you to know that up front. Okay? We will be done with the notes on Friday. So these 5 days are the entire chapter. Okay? 6 days. I guess we technically started on Friday. So we'll review on Monday and test on Tuesday. And that'll be your last test of term 3. All right, so adding probabilities. These two-way frequency charts, we saw some of these yesterday. And again, you're going to be given all of your information either in frequency charts or Venn diagrams. Those are pretty much the 2 ways that you're given information. So this particular one we're looking at, if we just kind of wrap our head around it for a second, we're exploring the differences in gender versus who's going to college and not going to college. And eventually we'll be able to see if there's a correlation. Are males more likely to go to college? Are females more likely to go to college? And we'll crunch numbers via probability to kind of compare those 2 variables to see if there's a correlation. That's where we're headed. But in the meantime, we have to kind of figure out how to read all this. So, a small high school surveyed 52 of its seniors. There's your grand total, 52, showing its face there. About their plans after they graduate. They found the following data and wanted to analyze it based on gender. In this case, if we pick a student at random, we can place them into one of 4 categories. They can be male, female, going to college, not going to college. And they'll always fall into 2 of those, right? Either they're male or female, so you'd have to check the box there. Going to college, not going to college, so you'd have to check the box there. So this is just asking you to read the table. What is the number of males? 30, yes? Who cares who's going to college or not going to college? The male total is 30. Natalie, the number of females? 22. Kate, the number going to college. Good. Lucas B, the number not going to college. 23. The number of those that are males and going to college. Jack B. Males and going to college. Nope. That's your number of males. That includes the ones, that includes the ones going to college and not. So just the males going to college. When you start using that word and, you're looking for who's doing both. Male and going to college is 16. Number of females and going to college, Alexa. Females going to college, 13. Good. Number of people who are either female or going to college. Female or going to college. Owen, how did you get that? So what numbers did you add? Yeah, there's only 52 kids total. So how many of those 52 are either female or going to college? Angie. So there's only one person that's not doing either of those things? Who's that one person? So you added the total number of females, which was 22, and you added the total number of people going to college, which was 29, and you got 51. Where's the flaw? She's on the right track. Where's the flaw? Chris Brooks? Right, so which category, Angie, did you double count? No, look at, I circled these three numbers, and I circled these three numbers. Which one got counted twice? The female who are going to college. That 13, you double counted. So your answer, that 51 that you gave me, is 13 over what it should be. You follow that? So this is where that or means addition, but you always have to subtract the probability that both happened, right? So that would be the number of females, which was 22, plus the number going to college, which was 29, minus the both category, which is the ones that you double counted were the 13 females who are also going to college. So subtract 13 off of that, and 22 plus 29 minus 13 is 38. So be careful with that. Because the other thought is, if she said 51, right? If you said 51 people are either female or going to college, that means you've only left one person to be male and not going to college, right? The males who are not going to college are the only ones you shouldn't be counting, if you think about it from that complementary standpoint. So this really includes everybody but these males who are not going to college. And so there's a second way you could do it. We're going to count everybody, all 52, except these 14. And that would bring you to 38 also. Does that make sense? Okay. Does someone have a question? I feel like I saw a hand. No. Okay. All right. What is the probability that a person picked at random would be female who is going to college? What, Mike Z? Female who is going to college. Female who is going to college, 13 over 52. Don't worry about the represent this using either a union or an intersection. Well, I'll tell you what they mean there. The intersection is the probability of female and going to college. That's really what that number is. I guess that's not so hard to wrap our head around, right? What is the probability that a person picked at random would be a female or someone who's going to college? Sierra with an S. The probability that a person picked at random would be a female or someone going to college. out of, because it's a probability, so 38 out of 52. Yeah, that's the conversation we just had. That was the part here from above. The number of people who were female or going to college was 38, so the probability is 38 out of 52. Good? So as a union, that's the probability of being female or going to college. And even though or means add, we know that that's the probability of being female plus the probability of going to college minus the probability of doing or being both, because we don't want to double count those. So I'm kind of already talking about it. We've talked about it yesterday. Why does the probability of F or C not just equal the probability of F plus C? Because when you just add the two individual probabilities together, you're double counting, is really what it is. You're double counting. You are double counting anybody who falls in both categories. And so the general law, and again, we've done this yesterday, and we're doing it again for OR, is to add those two probabilities, but then subtract off anybody that fell into both. And you're only subtracting them off one time because you double counted them. So it's not that you're not counting them at all, it's just that you're eliminating the double count. Any questions so far? Okay. Standard six-sided die is rolled once. Find the probability that the number rolled was either an even or a multiple of 3. So turned into notation, that's the probability of being even, or I'm just going to use M3 for multiple of 3. So we're going to look at the probability of being even plus the probability of being a multiple of 3. There's or meaning addition, minus the probability of being both. So how many even numbers are there on a six-sided die? 3. So 3 out of 6. If I want to look at my sample space for a single roll, there it is. So 3 out of 6 are even, plus how many multiples of 3 do we have, Bella? 2, just 3 and 6. Minus how many of those were both even and multiples of 3? 1, just 6, right? So 3, 6 plus 2, 6 is 5, 6. 5, 6 minus 1, 6 is 4, 6. Reduces to 2/3 is your probability. So that's just seeing that or property in action. Okay? Exercise 6. Insurance companies typically try to sell many different policies to the same customer. That's great, fluffy information to give us some context. At one such company, 56% have car insurance. 48 have home insurance. And 18% have both. I've been doing this a long time. You've been doing this a short time, but hopefully you'll get to this point. That screams Venn diagram. Because you've got two separate categories that have some overlap. Yes? You've got one circle for car insurance, one circle for home insurance. There are going to be people who have just car. There are going to be people who have just home. But there's also going to be a lot of people that have both. Yes? And this is actually easier than the other two we saw on the entrance ticket, because anytime they give you both, they've given you so much. They're already telling us the overlap is 18%. So if the car total is supposed to be 56, again, 56 is not showing up. I'm not writing the number 56 anywhere. 56 is what my car total circle should be. Yes? 18 of those are already accounted for. So the car is 56 minus the 18 that's already accounted for. That leaves me with 38% who just have car. So 56 is there, but it's just not verbatim and copied down. But those two car sections, just car versus car with home, have to add up to 56. Do we follow? And so same with home. If this is 48, subtract the 18 that's already accounted for, and that will leave you with 30% that just have homeowners insurance. And again, before I even read the question, what is that grand total percentage of people that are accounted for? 86, which means what percentage of people have neither of these policies? 14. So maybe those people have life insurance through this company or some other type of insurance. So find the probability that she or he has at least one. What's that answer? 86%. At least one. We're going to count this person, this section, and this section. They all have at least one. Some have more. Find the probability that he or she has neither. We already did that. 14%. Any questions? Flip her over. Okay. Conditional probability, arguably one of the most important things in the chapter. This is where we're going to have to start reaching beyond what you've ever done before. Because even and or probability you've done before, whether you realize it or not. So the notation, and we have the same chart that we were looking at before. The probability of being a female, just to catch up really quickly, is 22 out of 52. The probability of going to college is 29 out of 52. Okay, here's given probability. Here's the notation, first of all. It's P, and then in parentheses, it's C with this vertical line and F. What that means is the probability of going to college given you are a female. So what it also, if I rephrase that meaning, what that also can mean is, of all the females in this group, of all the females, what is the probability that you will be going to college if we already know that you're a female, okay? So here's the thing. If it's given that you're a female, we're only looking at the female category. So our total is something different. We're only looking at 22 people now. Out of those 22, how many are going to college? 13. So we just found that if you're a female, given that you're a female, you have a 13 out of 22, 0.59 is what that would be, chance of going to college. Is the overall chance of going to college that? No. If you're not looking at gender, 29 out of 52 go to college. That's 50.56. 29 out of 52 go to college total. But if you're a female, what appears to happen? Your chances of going to college go up or down? Up, it seems, right? Could be a coincidence, could be a correlation. But we do know that something about your chances of going to college is slightly better if you're a female. Does that make sense? So just to be clear what this format would be, your female, whatever stands alone, the given part goes on the denominator. And on top, you have to be both. And in this case, both would mean college and female. Does that make sense? It kind of lets us explore how these variables, in this case your gender, might be affecting your chances of going to college. Because your chances of going to college alone are 56%, if you're not looking at gender at all, versus if you're saying, okay, if you're female, then what are your chances of going to college? So you're still comparing in both cases the chances of going to college. It's just in one, when you're female, it seems to go up slightly based on this data from this population that we sampled. Doesn't mean that's going to be true for the whole world, right? It's just these are the 52 graduates in this particular school that were looked at. Okie doke. Really quickly, on the bottom, I'm not going to do these, but my denominator is going to come from which letter? M. And my numerator is going to be the probability of both. Versus this one, my denominator is going to come from C, and my numerator is going to be both. So this is saying, given that you're a male, what's your chance of going to college? And this one's saying, given that you're going to college already, what's your chance of being a male? Homework's coming once you get it out, as soon as you go. To the TLC, right? Mike, you know where you're going? Period 7, 166. And Jack, you are... I'm here, right? What period was that? 6. Come in the beginning, right? You want the whole period. And number 2 is my lunch, so I'm going to move it. I'll stick around if you don't.